There we go. So the final exam time of this class is from 8 a.m. to 10 a.m. on Tuesday, the 17th. And because the start time of the exam is actually 1 hour prior to the usual lecture time, you might need to make a special note because otherwise you go like, oh, okay, it starts at 9 a.m. No, if you come here at 9 a.m., you just lost an hour. So get your buddies to call you. But this stuff is, um, I don't know how you guys feel about it. Um, but after the talking enough about this, it really is a whole bunch of repetition of the same thing. Okay. So if your feeling is like, yep, yep, it's just tedious at this point, then yes, it is kind of tedious. Okay. Because tracking each and every register and what is on the stack, what you have already pushed, is kind of tedious. The checklist helps with the tedium of checking things, right? Because once you identify, oh, this is a conditional statement, I need to check this, this, and this. The checklist will go like, okay, make sure you check all the boxes, right? Or you're implementing a function, you need to have these things, these and these things. The checklist will help you with that too. Yes, correct. I don't see any other way of finding out what instructions are missing or which ones are extra. I don't think there are any other ways to do the same, do this, other ways to do this. But there's a pattern to that thing too. I mean, we always get the offset first, then we get to the address. There's no way to get around those two steps. Okay. Now, whether you need just the address or the value, that's kind of situational. Maybe just the address sometimes, and maybe the content sometimes. Hmm. I'm getting the offset to the beginning of the local variable, and I'm adding to it the offset to a member of that variable. That's perfectly okay. There's nothing wrong with that code. Hmm? It is combining two offsets, one to find the beginning point of the entire structure, which is the local variable, the other one to introduce the offset to the member that we need to access of that structure, perhaps, but you have to be able to read what I write. Hmm? Sorry? Um, well, if this is not making sense, it means you're not understanding what the labels are representing or how a structure as a local variable is stored on the stack. So those are the things that you might want to jot down and try to clarify to yourself because your question reflects that you are not quite understanding, either what the offsets are representing or that we n itself is a structure. And that structure is a local variable, which means it is at a certain offset from the base of the frame. So those are the things that you can look into. So I'm not trying to nitpick people. I'm just trying to deduce from the question that you ask, which part of what part of the material you might need to kind of revisit. Okay. Uh, that's possible, but what I'm saying is, this is computing the offset to n dot PV from the base of the frame. That's all it does. But it's just an offset. So in order to store something, I need the address. So in order to get the address of something that is on the frame, I need to add the base of the frame. The base of the frame is usually in the stack pointer. So that's why I can just add the stack pointer to the offset, but it's not an offset to a variable anymore. It is the offset to a part of a variable because that variable is a structure itself. Okay. Alrighty, so we are going to continue. Okay, we have just a little bit more of flip run, and then we have to get to main, and then we are all done. So not too much. Okay. All right. So we are now done with line 20 and moving on to line 21. So line 21 is right here. Okay, on line 160. Um, So once again, I am combining, okay, the offset to the variable n and the offset to a part of variable n together in one single expression. That is perfectly okay. But this is okay only because the offset n is representing a variable that is by itself a structure. Okay, so that's the only time when these two offsets can be combined in a single expression. So if that is the offset, then register D is still pointing to the base of the frame. So when I add the base of the frame to register C, now I have um, the address of Pn, and I store register B into where register C is pointing to. So now I have to ask, what did I put into register B? So in this case, register B ends up being ppos. So that is the correct thing. Register B has ppos. I store that to member Pn of the structure that is a local variable n. So this part is actually correct. Now, obviously, in this case, it also depends on which register you ended up using up here, to compute ppos itself. If you use a different register, let's say register C, then you probably have to fix this to use register C. It would not be considered in unnecessary change because the code does not indicate which register you really need to use. So in that case, as long as the way you use that register is consistent, it will still be counted as correct. All right, so now we're getting to almost the end here. Okay, so we now need to implement the actual recursive call. With this kind of program, you don't have to deal with what does it mean to do this, what is it actually doing to the data structure and stuff like that. You don't have to worry about any of that because there's no way you can run the C code. There's no way you can run the assembly code. Just do the translation. Okay, just do your best job making sure the translation is correct. So we are now down to line 22 of the C code, which means we have to push remaining -1 on the stack first because of the caller-callee agreement. So we get the expression or the label into register A, and then we decrement A right away. Is that correct? What are what are we missing here? Okay, we only have the offset, right? This is just the offset, so we are missing two instructions. We are missing the add AD, and then we are also missing LDAA. Because this one computes the address, this one gets to the actual value of remaining, and this one ends up calculating remaining -1. So I'm gonna have to say insert the following, insert the following. This ends up computing the address of remaining, and this one ends up actually putting remaining into register A, and now register A is remaining -1, and we can push it on the stack. But the code doesn't do any pushing right now. Well, maybe it'll push it later. Okay, so don't correct the code just yet. Okay, because you don't see the push right away. So now the first parameter is just pushing the address of local variable n on the stack. This is the offset to local variable n. This is the address of local variable n. This is dereferencing it. Ugh, I don't think the dereference should be here. So you have to take out the dereference here. Okay, so you say this is need a to be the address of n, not the first byte of n. So that's why you have to comment it out. Okay. And then we have decrement D store push A over here. So that means this A was never pushed. It was overwritten here right away. It was never pushed. So that means I kind of need to push it on the stack first. So now you have to say insert the following code to push A on the stack, to push remaining -1. Okay, so that's going to be decrement D and stda. But that means one more thing, okay? Because that means by the time we get to line 175, register D is not pointing at the base of the frame anymore because the frame of the base is still at the same place. But at that point, we would have remaining -1 also pushed on the stack, and the stack pointer will be now pointing to 1 byte below the base of the frame. Is that okay? So the way we compute the address of something that is on the frame need to account for that one extra thing that is pushed on the stack. You can account for that by doing a 1+ here, okay? And you have to explain, because remaining -1 is pushed so that the stack pointer is pointing to 1 byte below the base of the frame. You can also do the same adjustment by using an increment A over here. Okay, after this instruction or before is fine too, but you have to only do one or the other because the objective is the address is 1 byte off, so we have to adjust for that 1 byte off. Now, how do you add that extra one in? You can add it in using the register, excuse me, using the immediate constant, just add one to the constant, or you can use an increment A instruction as long as you do it before the store instruction. Is that okay? So personally, I prefer this solution because it's more efficient. I'm not adding more instructions. I'm just making the expression a little bit more complicated. If you have expressions getting a little bit more complicated, it uses up additional assemble time, but it doesn't use any runtime. So that's why it is quote unquote a preferred way of doing things if you have a choice. All right, and then we push the return address on the stack here, which is typical, and then we do a JMPI to flip run. And when it comes back, the return value, which is going to be the return value that this invocation has to return, is already in register A, so there's nothing to do with register A here. But I think I'm forgetting something here. What am I forgetting? Uh, Arguments. Yep, it's the arguments, okay? Because this is a function called I pushed these 2 bytes as arguments. It is the responsibility of the caller to clear or to deallocate the space used by the arguments. So I need to increment these over here. Okay, I'm going to add a comment here. Insert the following code to deallocate space used by arguments and inserted code. There we go. Now, once again, if you do it on a piece of paper, it is actually easier, okay? But since I'm doing it inside the dumb text editor, this is the only way I can emphasize that this is the code that is inserted. All right, so are we still doing okay? Okay, all right. So now we go to the C code, scroll down a little bit, go to main, okay? So we're almost done here. Because we checked this code already earlier, okay? Because I did the structure check, so I checked this code already, and I need to say insert the following to continue execution at caller, which is a JMPB instruction. Okay, I forgot to mention that earlier. So now we have to look at main and see, check out its implementation. All right, so main has a local variable a, which is of array size. It has another structure as a local variable, which is called first, and that's the C code. And in the assembly code, I put first, and then A is main first 1 plus, and then LVS is A array size 1 times plus. So that is incorrect, okay? Now, the ordering within the local variables, there's no agreement whatsoever, okay? As long as you use it consistently and there's enough space for all the local variables, it's fine, okay? In other words, it is okay to have local variable first to be at a lower location compared to local variable A. That is not a problem. The problem has to do with how much space did I allocate for the local variable first. I only allocated 1 byte here. That is not correct because that needs to be R size. Because first, as a local variable, is not a pointer to a structure, it is a pointer. So we have to say change 1 to R size because first is a structure. It's a struct R. Is that okay? All right. And then this one is not wrong, okay? There's a lot of computation that is not necessary, but it is not wrong because A as an array has array size number of elements. Each element is only 1 byte long, so that means if I multiply array size by 1, that will give me the total size in terms of number of bytes that array A will need. That means I can add that product to the offset to main A to compute the size or the number of bytes I need for local variables. So that line is fine. So once again, I check the beginning, I check the end, and right here, I check here, go like, hey, this is just 1/2 of what I need because I need to allocate the space for the local variables. So I have to insert the following to allocate space for local variables, which is a subtraction in this case. And the way that I do things is I check the beginning and then I check the end. So the end is actually correct, not a problem. And then the return is also correct here. So remember the checklist thing? These are good things to put on the checklist. All right, so if that is checked, then I can move on to start with the first statement here on line 33. So the way it is done is I put the offset to local variable A into register A. I add the base of the frame to register A. So register A now has the address of the entire array, which also turns out to be the address of element 0. And then I put a 1 into register B, and then I store B, which is the 1, into where register is pointing to. I think that's fine. That is, in fact, storing a value of 1 to element 0 of array A. Okay, that's good. And I increment A, so that means A is now pointing to the second element of array A. And then I load 4 into register B, store register B into register A. That will accomplish A bracket 1 gets 4. And then this is kind of the same deal, okay? Increment A again. So A is now pointing to the third element of array A. And I put a B, 5 into B. 5B is stored to where register is pointing to. So these are all fine. And now I move on to line 36. So line 36 is storing the address of the first element of array A to the member PV of the local variable first, which is a struct R. All right, so first we compute the right-hand side. So main A is the offset to the entire array. 1 times is Okay, 0, 1 times. Okay, so this 0 refers to the index. This one refers to how many bytes each element is going to consume. And this multiplication will give me the offset to a specific member in the array. And then the plus is going to add the offset of the member from the beginning of the array to the offset of the array itself, which gives me the offset of a particular element in the array. So that part is actually done correctly. And then I add the stack pointer, which is the base of the frame, to the offset of a particular element in array A, which ends up as the address of a particular element of array A, and therefore accomplishing the right-hand side of line 36 of the C code. And then the rest is computing the offset of member PV of the structure that is first. Okay, first is the name of the structure because it's a local variable. So that part is done correctly. And then adding register D, which is the stack pointer, which is also the base of the frame, to register B will compute the address of member PV of the structure first. So that is also done correctly. Do the store. So that's all good. Sub AA, makes an A0, and then we compute the offset to member PN of the structure first, okay, and put it into register B, and then we add the frame of the address of the frame or the base of the frame to register B, which ends up with the address of member PN of the structure first, and then do the store. That is also done correctly. So now we are down to the very last statement of the entire program. Okay. So this one is a little bit harder to see because it wraps around here. So let me see if I can get rid of the unnecessary space so you can see the nesting a little bit easier. Okay, I think that's better. So now we have to look at the function call to flip run. This parenthesis is matching this parenthesis here. So this is the function call. The plus one is at the very end. We're supposed to add one to the return value. That's basically what it is. So the second argument is this entire thing here. This is the entire second argument. So now we have to say, are we pushing this on the stack correctly? So now we look at this entire expression and go like, okay, where do we start with this thing? Well, we can start with PV, the value of PV as a member of first. Okay, so we'll start with that. And that's where this assembly code is starting. So we load the offset first into register A. We add the base of the frame to register A. So we have the address of the structure. This is the offset to the member. We add the offset of the member to the address of the structure, ending up with the address of the member. And then we do an LD instruction here to get to the value of member PV of the structure first. So this is all done correctly. We are accomplishing basically this portion here from lines 244 to line 248. Line 249 is computing the address or the offset from the frame, from the base of the frame to um, element 0 of array A. This 0 refers to element 0. This one refers to the size of each element in the array. And then the product of that is the offset to member 0 in the array. But I'm adding that offset to the offset of A itself, ending up with the offset to member 0 of the entire array. And then I add that also to array size because that's what the code is requesting. But this is not supposed to be an add, it is supposed to be a subtraction. So that means the outermost subtraction is incorrect. This one is supposed, or it should be a subtraction, not an addition. So we can say that the C code specifies a subtraction. So that's the correction. And then push it on the stack. Wait, wait. Okay, sub AB. Sub AB. What are we subtracting? Okay, okay, I see. Hmm. So register A has that thing, and then we decrement that. So this decrement A is referring to this decrement here. So, oh, okay, I see it. Okay, this plus is not wrong. This plus is actually not wrong. Okay, I'll explain it. It's algebra. Okay, it is algebra. So of this entire expression here, okay, not counting this, minus one, of this entire expression, which part is static? In other words, which part the assembler itself can figure out? It's like, yeah, I know how to get that. Mm. So the offset from the base of the frame to element 0 of array A is static. Okay, let me say that one more time. The offset from the beginning of the frame to element 0 of array A is computable just by the assembler because it's not a runtime thing, because I'm just talking about the offset. Now, I understand that the address of this thing has two components because you also need to add the frame, the base of the frame to the whole thing. So we can separate that out. Array size is just a label, okay? It's just 3 for the most part. So that means array size plus the offset to member 0 of array A can be added together in a static way. And that's what line 249 is doing. That's the static part that can be computed without actually accessing anything from the stack. But the actual address involves adding the base of the frame. So we have to add the stack pointer to this whole thing in order to get to this address here. And then the register A contains the value of PV. So that means the subtraction here is missing one thing. It is missing, this is a subtraction. This is also a subtraction. So we need to add the stack pointer. So that means we need to add BD here, okay, and add it to accomplish the, okay. So I'll make it very clear. This is array size plus the address of A bracket 0. Okay, is that okay? So once B is array size plus the address of A bracket 0, then we have to subtract the PV member or the value of PV member of first from the whole thing. So that means in the next instruction, it is reversed. Okay, the sub AB should be sub BA. So this one should be changed to sub BA. And then the decrement A is just performing this particular decrement here. But then if we switch the register, we also have to switch this. So this is also changed to decrement B. And then we push that on the stack, decrement D, and then we push register B on the stack. Okay, there we go. And then we have to push the address of first on the stack. But at this point, once again, we have one extra item on the stack. So that means, in order to compute the address of first, we have to add 1 to the offset. So now we have to do a 1 plus and add 1 plus because an argument is pushed already at this point. Get to the address, push the address on the stack, and then we push the return address on the stack, call the function, decrement D, increment D to deallocate the two arguments. Increment A because of this +1 over here, and then store that to PV, the member PV of first as a local variable. So this time I do it in a slightly different way. Register B is the offset to the structure, and then register C is the offset to the specific member. So this time, instead of adding these two in an expression, I use actual instructions to perform the addition, which is okay. It is just inefficient, but it can be done this way too. And then at the end of line 268, register B will contain the offset to member PV of the structure that we know as local variable first. But because it's still an offset of something that is on the frame, we have to add the address of the frame, which is register D, to that offset. That becomes the address of member PV of the structure called first as a local variable. Register A already has the correct result to store because it's the return value +1. And so the store instruction will finish the last portion of the entire program. So I think the trickiest part is the algebra of this portion. So let me just kind of expand on that a little bit. Okay. Okay, so I'll expand over here. Okay. So array size minus first dot PV minus the address of A bracket 0, and then the whole thing minus 1. Okay. So this is computed. So basically, I separate it into two parts. The this whole thing, because I'm looking at the address of the address of member 0, element 0 of the array A. So this is broken up into two parts. It's broken up into the part of the frame base plus offset to A bracket 0. So I broke that up into two parts. The offset to A bracket 0 is constant. So that means I can basically do the subtraction. Actually, it is the addition here. So because this is a subtraction and this is a subtraction, so they turn into an addition. So now I take that off here, offset to A bracket 0. So I put that addition here and then take it out from inside here. And I'm missing one paren, which is here. Okay. So is that part okay? Just in terms of algebra, I took this one here, which is just a constant, into here. But because this is a subtraction inside the subtraction, so this value is actually added to array size. And because array size is just a label, this can be expressed as a RPN or reverse Polish notation using only constants. So they're grouped together. And that is what we computed on line 249. So this portion, this entire thing is computed by 249, line 249. So the rest is dynamic, which means the rest is the stack pointer. So this is actually the stack pointer, but because it is also double subtraction, so that means the whole thing becomes this thing, and then I have to add the stack pointer, which is in register D. So by doing that, I take this entire thing out. So that's why I have to subtract the value of PV member of local variable first from the sum of the stack pointer and this entire thing, and then just subtract one at the very end. So the subtraction of 1 could also have been folded into this entire calculation, but the code is not wrong to use a decrement A afterwards. So that part is not wrong either. So that's pretty much the entire program. Okay, so any questions, comments? I think there are bugs that are fairly easy to spot. Okay, the extra dereference, that sort of thing, they're easy to spot. And then this algebra thing, maybe a little bit hairy. Um, the other one that are easy to spot is the 1 plus. Okay, if I have already pushed something on the stack, then you have to adjust the offset by 1. So I think those are fairly easy to spot as well. You just have to make a note. Okay, when I push something, when I try to compute the address of something, where is the stack pointer pointing? Are we sure that the stack pointer is still pointing at the base of the frame, which is usually what it does? Or have I pushed something on the stack already? Because either one, I need to save something on the stack, like in the recursive program, or I am in the process of pushing arguments on the stack, and therefore the stack pointer is below the frame, the base of the frame. So you have to keep track of where the stack pointer is pointing to. So I think those are fairly easy, or once you have a checklist, you can spot those. There will be some variety of using perhaps, okay, using the wrong JCI versus JLI, okay, so those are fairly common. The label, branching to the wrong label, okay, that's also something I can ask. Missing dereferences, too many dereferences, those are also fairly common because I'm testing whether you know what is in the register as opposed to what should be in the register. So how many times do you have to dereference to get to something that we need? So you have to keep track of that. Um, that's about it. So how are you strategizing your preparation for the final exam? Hmm? Okay, so reviewing the programs can be helpful, okay, but you have to identify the concepts that you need to understand. There are only a few concepts that we have to understand. The caller-callee agreement is big, okay, that's important. Two, how do we translate control structures like loops and conditional statements into assembly language? That is also important. How do we utilize structures? That's also important. Now, the combination and the interaction between array indexing, structures, and pointers, those are really just remixing of certain things that we have already mentioned. Do you understand the concept of a pointer or an address? Okay, if you get that, then it's good. Okay, do you know how to dereference something? Even if the pointer is dereferencing to a structure. Okay, if you understand the concept, then we are good. But most of the time, we don't need to dereference to the entire structure. Most of the time, we want to access a particular member of a structure. So now the question is, if you have the address of the structure already, and you know the offset to a certain member of that structure, do you know how to find the address of that member? And do you know how to find the value of that member? So those are all basically individual concepts, and the exam is really just trying to recombine those individual pieces in a certain way that go like, okay, in this particular sequence of using these concepts in this particular order, do you know how to figure this out? So the beauty is you don't have to figure out things on your own. So you don't have to ask the question of how do I get started? The bad news is you have to read my code. So you kind of have to think about, okay, so how do we do this, right? How do I read tax code? The key is tracking what is on the stack, tracking what is in each register, and tracking how do I end up here? Okay, did I end up here because it's just the code falling through here, or did I end up here because of an explicit jump instruction? If it is from a jump instruction, what does it mean if I end up here? What registers might have been set up already in what way if I end up here. So once again, it boils down to tracking the registers, tracking the execution thread. How can I possibly end up here? What can I assume if I end up here? So that's, hmm? Yes. So everything uses the C code as a reference. So the C code tells you what the code is supposed to do. The assembly code is an attempt to get it done, but incorrectly. You have to figure out which part is incorrect and tell me about it and how you're going to fix it. If you have a study group, this is one thing you can potentially do. I'm not saying that you have to do it. If you have a study group with a few people in it, okay, you can have one person, okay. Let's say you have a group of 3 people, A, B, and C. So in the first round, okay, you say person A, you'll be the person making the question. You can take one of the many sample programs that we have done so far, okay, and then person A is just go like, okay, let me see what tricky way I can mess up this program. Take out this instruction, change this one a little bit over here. Aha, I'm going to use the wrong register in this instruction. Okay. And then present that to person B and person C and go like, okay, go fix this. Now, the nice thing about that is we know, okay, person A knows what the program is supposed to be. So there's a solution built in. The question is, can person B and person C spot the problems and say, okay, there's a problem here, there's a problem here, and so on. So then they can take turn. Okay, the next program, person B is the person who's gonna mess up the original code, and then person A and person C will have to try to figure it out, and then person C will assume the role of making the puzzle, and then person A and B will be the ones solving the puzzle. So that's why having a study group can potentially be helpful, because this way you can kind of rotate the responsibilities, and different people have a different way of messing up a program too. Okay, some people say, "Oh, I just love dereferencing. Too many, too little, not enough." Okay, I'm gonna mess around with dereferencing or the LDAA instruction. I'm gonna put one extra one here because there's one here already, but I'm gonna put an extra one here, and or there's another one here, or there's not supposed to be one here. I'll stash one over here. Okay, some other people like branch instructions and just go to the wrong label. Okay, some people like JCI versus JLI and kind of mess those up. Okay, so that can be helpful because the key is you have the solution. It's not like I don't know what the answer is supposed to be. Yeah, we know what the answer is supposed to be. It's just can you catch what is wrong with the program? So having a study group can potentially be useful. I'm not sure whether ChatGPT can do this. You can present a program that is correct and ask ChatGPT to mess it up intentionally so that it can test you whether you can find all the flaws. You can give it a try. I haven't tried it yet, but I keep getting surprised by what the tutor bot can do. All right. So is this helping you with your homework assignment? Okay, it should, because your homework assignment actually has less complicated constructs compared to this program. So if you can master all the concepts of this particular program, your homework assignment, the only difficulty of your homework assignment is if you make one tiny little mistake, okay, then it's going to blow up. So the key is to do it slowly. So every time you add something, you're only adding 5, 10 lines of code. So if you know that it's blowing up, it's most likely because of the last 10 lines that you added to the program. So that's the best way to limit what kind of error you can be making in terms of the scope. All right. So other than that, I don't have anything else to add. And we still have another 35 minutes. So I'll stay here as long as somebody has questions to ask. But as far as the lecture is concerned, it is done.